Good afternoon. I am Mr. Ish. Thank you for joining me for this very exciting video. I promise you a very exciting video here. Why? Because we have a specific task which is challenging and calculator is not allowed by any means. We have to find a single point x comma y, a coordinate pair on this function f of x equals cosine hx, hyperbolic cosine, such that at that point if you were to draw a tangent line, the slope of that tangent line would be equal to 1. Let's visualize our problem. We have here a y-intercept 0, 1. It is a y-intercept for your hyperbolic cosine. The graph looks something like this, very well mirroring the secant x function curve. Anyhow, if you're looking at all the points here from minus infinity going up to 0, all these tangent lines would always have a negative slope. Think about it. These lines would be aimed downwards. At a point 0, if you draw a tangent line, the slope will be equal to 0. It is after 0 going up to infinity, not including 0, but going from 0 up to infinity somewhere, that these positive tangent lines will arise. And you can see them visually, all these lines have an upward slope. At which of these points, x comma y, is that slope of that tangent line equals to 1? That right there is our problem. And we cannot use a calculator, as I've said it. No calculator absolutely allowed. How do you go about doing it? We have a function here, f of x is equal to a hyperbolic cosine. That's our function. You know, when you've done the derivative of a function using the basic templates of derivatives, when you do a derivative, you have an f of x, you've derived this derivative of that f of x. What you end up here is kind of a template into which you plug in your x or your y or both based on explicit or implicit differentiation. You plug in your x value and that gives you your slope of your tangent line. Our problem is not too hard here. It's the part which comes after the determination of the derivative where when we cannot use a calculator, the problem arises. So we have a specific function here, hyperbolic cosine. Its derivative is so easy. That right there is not even our challenge. We know our function is f of x. In terms of its derivative, we know our derivative is going to equal sine hx. This right here represents our derivative. It is into sine hx. If you were to plug in a specific value here, x, you should have a value of 1, which would represent your slope of your tangent line. But how can we do this without using the calculator? You know, when you're looking at this specific expression here, the derivative, plugged into it a specific x value such that you'll get a value of 1. Here x would be equal to inverse hyperbolic sine. See, inverse hyperbolic sine of this 1. But we cannot use calculator, so what do we do over here? That right there in the remainder of this video is our challenge. Determining this x-axis value will not be hard. It's a determination of the y value which will create us a little bit of a challenge. We've already determined that for this function cosine hx, its derivative in terms of the template is sine hx. What we have to do is now determine the x-axis value of this sine hx. At what value at x will we get a 1 in terms of our tangent line? We know the definition of the sine hx is e to the x minus e to the minus x over 2 is equal to 1. Solve for this x, and we cannot use a calculator. E to the x minus e to the minus x is equal to 2. E to the x minus 1 over e to the x is equal to 2. Common denominator, e to the 2x minus 1 over e to the x is equal to 2. Take this e to the x on the other side. E to the 2x minus 1 is equal to 2 e to the x. Bring everything on one side and create a quadratic style of equation. E to the 2x minus 2 e to the x minus 1 equals 0. Substitution, u is equal to e to the x. We're looking here at u square minus 2u minus 1. Bring the quadratic formula, minus b plus minus square root b square minus 4ac divided by 2a. Again, calculator not allowed. A is equal to 1, b is equal to minus 2, c is equal to minus 1. Let's put our values here into the quadratic formula. Minus 2 is our minus b. 2 plus minus b square in the root minus 4ac, our discriminant over here. 4 minus 4 times 1 times minus 1 divided by 2a. What do we get? 2 plus minus root of 8. We get 2 plus minus 2 root 2 over 2, which equals to what? 1 plus minus root 2. All of this easily establishes that in terms of this is my value, u is equal to 1 plus minus root 2. But that's what u is equal to, which is e to the x is equal to that. What we have to do is now solve for that in terms of the natural log. and you know you're not going to bring in a negative value, e to the x is equal to 1 plus minus root 2. We're continuing on from there. You can eliminate the negative value because when you take the x, you take the e on the other side, you're bringing in natural log 1 plus minus root 2. But you can't do a natural log of a negative number. This must go away. Our x-axis value here is this. X is equal to 1 plus root 2 in terms of the natural log. This right here is my x-axis value right over here determined. In terms of meaning, it doesn't look very meaningful, right? You're not getting a good calculator value, but this right here is our very legitimate x-axis value for x comma y. Now how do we determine the y value? Up till now, we've come up to this value here, which I'm going to say if x is equal to natural log 1 plus root 2. The determination of that y value is going to be our work, especially because calculator is not allowed. Let's save our work. Let's create some space. We know our function f of x is a hyperbolic cosine. We've determined the x coordinate. We have to determine the y coordinate where the tangent line will have a slope m is equal to 1. How do we go about doing that? Now we come back to our original function. Our work with the sin hx in terms of the derivative is complete. We have to come back to the hyperbolic cosine function. We know now that we're coming back to this hyperbolic cosine hx. If you were to take this value right over here and plug it in here, this is all going to equal to your f of x, which is equal to y. At this specific x-axis value, which is natural log 1 plus root 2, if you were to plug that into your hyperbolic cosine, you'll get your output here in terms of your range, which is your y value, and that will very well give you that y value of that x-y pair. But how do we do this? Come back to this, e to the x plus e to the minus x. This is the definition of your hyperbolic cosine. This is equal to y. Now you plug in your x-axis value in places of these x, e to the power of natural log 1 plus root 2 plus e to the power of minus natural log 1 plus root 2 all over 2 should equal to that y value that we're calculating and that we're trying to determine. Again, we can't bring in a calculator over here. We cannot. Otherwise the fun is gone. How do we go about solving this? I will refer you here to my video I presented not too long verifying natural log identities, and I'll post a link and tag to that video in this. And you know there's a specific identity, e to the power of natural log x is always equal to the x. E to the power of minus natural log x is always equal to 1 over x. That's exactly what you have over here. Here's my natural log, here's my x component, here's my minus natural log and my x component. This right here, e to the power of ln 1 plus root 2 based on this will become just 1 plus root 2. The e to the power of natural log goes away. You're left only with the exponent that comes down as a base. Plus, you have over here e to the power of minus natural log 1 plus root 2. Based on this, it'll become 1 over 1 plus root 2. And then you know at the very bottom you have this 2 sitting. Do a common denominator. Remember, we're doing all of this now to determine our y value. You have a common denominator of 1 plus root 2, which is again sitting all over a 2. I can bring this 2 right here into a denominator along with this denominator. You can just bring it up because this is really a 2 over 1. It flips and you have this. This 1 goes in 1 plus root 2, 1 plus root 2 times. You're going to have 1 plus root 2 times 1 plus root 2. And remember, I've brought this 2, but after having done this operation. 1 plus root 2 goes in this 1 time, so you have that. You have to open this up. When you open this up, what are you going to get? You'll get 1 plus 2 plus 2 root 2. A plus b times a plus b is equal to a squared plus b squared plus 2ab plus 1 over 2. You don't need to open that 1 plus root 2. What do we get here on the top? We have a 4 plus 2 root 2 over 2 into 1 plus root 2. Isolate a 2 here in the numerator. You have a 2 parentheses 2 plus root 2 divided by 2 over 1 plus root 2. Well, these cancel out. You're basically left with 2 plus root 2 divided by 1 plus root 2. All of this is equal to y. If you could, by some miracle, simplify this, you'll get your easy y value, which is this we're determining. How can we simplify it? Well, I need to simplify it, but I need space. What I'm going to do is create my space right over here, and then we'll do the simplification. 2 plus root 2 over 1 plus root 2, rationalize it, the denominator, 1 minus root 2 and 1 minus root 2. Do your computation here in the top. You'll have 2 minus 2 root 2 plus root 2 minus 2. The conjugates will multiply. You'll have no intermediate terms, 1 minus 2. Simplify it. This 2 and this minus 2 cancel out. You have minus 2 root 2 plus root 2, which is a minus root 2 divided by minus 1, which is equal to root 2. which is equal to my y value. And now I know my y value is equal to root 2. So now when the question asks find the x comma y value where f of x hyperbolic cosine has a tangent line slope such that that tangent line will have a slope of 1, what is your answer? Your answer is this: natural log parentheses 1 plus root 2 comma root 2. And why don't we just post this answer right over here for a good clarity? Our answer is this in an xy coordinate pair form: natural log 1 plus root 2 comma root 2. This right here is our answer. Now let's bring in the calculator and verify all of this in a matter of a few seconds. We have to find, originally we determined from the derivative hyperbolic sign we needed a value of x such that it was equal to 1. Put your 1, invoke the shift inverse hyperbolic sign, you get your 0.881373. If you do natural log 1 plus root 2, we'll have exactly that: 1 plus 2 root natural log, I have 0.88137, which is equal to that and what we've obtained by our calculator. Now how would you determine this value? Well, this value would come right here into place of your hyperbolic cosine. In place of the x you get your output. Let's take that value again: 1 plus 2 root natural log, invoke the hyperbolic, no more inverse, just the hyperbolic and cosine, and we get 1.4142, which is root 2. Take 2 and root it and you get 1.4142 and you're done. So this entire question without the calculator is indeed a challenge, and this challenge in itself was exciting. You have to start with the hyperbolic cosine, determine its derivative. From the derivative you determine the x-axis value when you have this slope given. Remember, when you have a derivative determined in terms of its template, you put in your known x-axis value and you get your slope of your tangent line, especially when you're dealing with explicit differentiation, which is what we were doing here. Except here we had the slope of the tangent line, we just had to calculate the x-axis which generated that. And again, you know how that happened. I showed you the procedure. It brought in that quadratic equation, and from that quadratic equation we got this single value because the negative value was removed, because you can't do a natural log of a negative, but you can do this. From this value here to determine the y value, you have to employ it here into the hyperbolic cosine in the places of x in its definition form, which brought us through this entire procedure. And at the end of that procedure we got this little expression over here: 2 plus root 2 divided by 1 plus root 2, which when you rationalize it you got your y value of root 2, and the procedure has been completed. Here's my x-axis value, here's my y-axis value for that coordinate pair for the hyperbolic cosine where the tangent line will have a slope of 1, and this answer here should be good. And with that, I thank you for watching this video. Stay tuned for more interesting videos on the way. Have a good day.